Afternoon, everyone. We are exploring the adapting of roads for machines next. Can I welcome Andy Fish of 3M up on the stage, please?
Okay, adapting roads for machine vision. I've got about 15 minutes, so this is going to be fairly quick and fairly high level. This is obviously a very complicated subject. I'm sure you've seen a few other presentations around. So I'm going to try and bring this back to basics, really, and some simple science. So start with the automobile revolution, really. If you look at cars and how they are now, they're very different to how they were when they were first invented, with the original patented Benz Motorwagen there. Over to the right there, something much more high-tech, with a lot more software and hardware than it used to have. Interestingly enough, you think about it, the car's changed a lot. The human hasn't really. We still rely on the human eyeball, Mark I. Still the same, pretty much. Does the same job, and we still have to do that tedious function of driving. Whereas the vehicle, hardware and software, has changed a great deal, and still is. So what's the difference between human vision and machine vision? What's the difference? How do we figure that one out? Well, we both rely on the same kind of cues. We rely on light, and we rely on seeing objects. Most autonomous vehicles will have camera systems, machine vision systems, to distinguish what's around them. We have our eyeballs, and we have our common sense. Well, if you drive around the M25 on a Friday night, maybe not so much common sense. Talking of automated vehicles, I'm sure you've seen some of this and variations of these descriptions before. You've got a couple of different types of systems, realistically. You've got things you can consider to be a connected vehicle. Realistically, my vehicle currently is a connected vehicle. I have a sat-nav system that connects to the cloud and gets traffic data in real time. That gives me some assistance. It's a connected vehicle. Then you've got what you might class as an autonomous vehicle, something that operates completely in isolation to everything around it, but uses sensors to find its way and to give you information. And then to the far right, what everyone calls a CAV, a connected and autonomous vehicle, something that uses both those technologies. Again, a well-used and well-understood system here. Generally accepted, there are actually 6 levels, if you like, of automation, 0 being none, so I'll discount that from my slide for space. Level 1 is very much here today, isn't it? Driver assistance, things like lane keeping assist, sign recognition, they're all level 1 kind of technologies. It informs the driver and hopefully helps the driver. Level 2 is partial automation, so this is where the vehicle can assist you physically, I would suggest. So things like automatic braking, adaptive cruise control. The car is actually doing something. It's overriding you, potentially. Then you've got 3, which is the tricky bit, where it gets a bit more difficult, and that's conditional automation. So when vehicles can do a lot of the tasks under certain circumstances. Clearly, there are challenges for that. And then over to the right further, level 4, which is a lot more complex. This is high automation. This is when the vehicle can pretty much drive itself over many scenarios, but still not everyone. And level 5 being the utopia of full automation, when the vehicle can drive itself without any real other input. The way I kind of summarize that, level 2, that's feet off really, isn't it? Feet off the pedals, the car does itself. Level 3 is a bit more like hands off, whereas level 5 is brain off. You're not really a driver, you're a passenger. Maybe they'll invent a new verb, maybe you'll be a rider, I don't know. There are challenges for these things. Inclement weather, poor road markings, poor signage, the infrastructure itself affects those first few levels because they are just reliant on the same visual cues as we are. When you get further along the spectrum, you get to connected vehicles, and then you have other problems. So common standards. If these vehicles are talking to infrastructure, talking to themselves, and communicating up to the cloud, there needs to be some common standards. And of course, with that comes security. That's not a subject I'll cover today, I'm sure you'll be glad to hear, but it needs to be borne in mind. It's different challenges, but really we need to get to level 3 fairly quickly because vehicles are ready for it now. So why is the infrastructure important? Why is that such a challenge, and what makes a difference? Well, it goes back to the whole point of humans and machines needing the same basic inputs. If my slide will continue to next. Hey. So just take a few examples of a couple of bits of infrastructure that might be confusing to humans and to machines. This one, is that a nice piece of signage? You'd hope that a human driver might look at the give way sign and realize that's the important one. A machine will have to be taught that. if it's reliant on signs alone. If not, it has to become somehow already a connected vehicle because it needs to know by other means, perhaps GPS, to know what the speed limit is. This one, is this good for humans and drivers? It's okay, you can say, no, that's really bad taste. It's there, but there's a reason why that's slightly funny. That's part of the science, it's why it's there. We'll come back to this one. This one, it's an interesting one. Good sign or not? I hope automated vehicles have spell check. But actually, it's mindful that automated vehicles are okay in normal situations, but if you think about a temporary situation, a vehicle needs to understand that circumstance. It needs to understand it there and then. So if that sign has just been put out as an emergency, and there's no electronic signal to the vehicle to understand there's a road closure, it may need to rely on things like signage and understanding there's an extra month in the year called Septamoeba. I hope also automated vehicles are not too judgmental. It's not going to take you on a left-hand turn thinking that this is not going to be very interesting for you. There's a very long story behind this. I do it in many of my other webinars. Do tune in to see them. And the last one, my least favorite sign of all time. Sign not in use. I hope an automated vehicle hasn't got eyeballs to roll and doesn't tut out loud when I see this. There's a reason we find some of these a bit funny and amusing why they're there, and that's because there's science. The CIE did a study. It's study number 74 if you want to look it up. It was a groundbreaking piece of work, and it's just pure common sense. In order for a traffic sign, road marking, or anything on the infrastructure to be valuable to a driver, we need these 4 things in this order. If they don't come in this order, you don't get the right output. So you need conspicuity, first thing. We need to attract attention. If we can't see it, we don't go on to the next stage. So once we've actually seen it, it has to be legible. We have to be able to read it. And that's in all conditions. And that's the same is true of machines and of humans. Once you've read it, you have to go on to comprehending it, understanding it, because reading and understanding are 2 very different processes. So I can read that sign, I've got no idea where it's taking me. Hopefully an automated vehicle will make more sense. The last bit is the bit that humans do that's slightly different to machines, and that's why some of those signs are a little bit funny while they're there, and that's credibility. We look at the sign and we look at the infrastructure around us and we understand whether or not that's valid. So we could see this sign and take no notice. It would be ironic if Winnie the Pooh came down and landed on your bonnet, but nonetheless, we do that process automatically. A machine has to do that, gains credibility by learning. It has to look at its surroundings, and it has to be taught, because that's how we get credibility, from experience. And a machine has to get experience by a learning process. Just highlighting what affects these things on a macro scale. There are many. I've really tried to boil this down to make it work in 15 minutes. The first 2 stages are the most important. Certainly for nighttime driving, reflectivity. We need to be able to see the reflection of the car's headlights for us to see it. And again, an automated vehicle needs the object to be bright enough so it's got more bright pixels to see on its camera than it does dark, and then it decides what the image is. Color and transmissivity also affected. Design, placement, and relevance are a bit more to do with the engineer placing the signs. That's more to do with law and what the law says we can place and how it should look. So if you overlay that with how a machine basically functions when doing this, you can see the first part of a machine there in red, object detection. First thing it has to do is recognize the object. That's why it needs to be conspicuous. The next part is the recognition of the object, which is partly processing, really, but it needs to understand it to know what to do and how to make a decision. Then it will process it. That's our part of comprehension. That's understanding. And the last part of the machine's journey there is the decision. What comes out of the algorithm? When you put all that data in, what comes out the other end? That's where we differ slightly to machines, because our credibility part of it is really part of our decision-making process, and actually the decision and credibility for a car comes from processing. Just to highlight the point about conspicuity, those little images at the bottom, you can see the differences here for a road user. So over there on the left, we have a nice daytime picture. Very easy. If you take a picture of that, you can analyze those pixels if you're a machine, or those pixels if you're a human, and determine where the white lines are, where the yellow lines are, and where that arrow goes. In the middle, you've got the same view at night. It's actually not bad. We can do the same. It's arguably easier for a machine at night because we've got more contrast, except when it rains. The road marking there is gone invisible because the water is laying on the surface, and therefore you've lost all of that contrast. So simple things like that can fool a basic technology like a lane keeping assistance. Not all of them, but some of them, clearly. So looking at that process, thinking about that as we've just gone through, if you look at the image on the left, as we've said, humans are very good at reading between the lines, or even reading the lines, I should say. We can determine what road we should follow, what lines are relevant for us to follow. If they're not clear for a machine, it needs to go through another process, possibly use other sensors, not just machine vision. And maybe it's using the surroundings, GPS, whatever it's using, you're now having to add other systems in order to interpret what's going on. A good example here was an image I got. So if you were to imagine this is a vision system, this is purely hypothetical, there's an image of the road there. You can see these nice straight line markings there, and then there's a nice marking coming in diagonally straight towards that car. An automated vehicle needs to look at these markings. They look contradictory. It has to understand which is the correct one. So already, if you're just relying on an image, you start to have to think, like we do. We would look at this and we would go, where are the other cars going? What other visual clues are there around for me to make a decision? A machine has to learn that or use another array of sensors to determine the correct action. So we start to get into the point where we really do need intelligence. So can a machine make that decision correctly with its intelligence? How intelligent can we make the machine? Actually, they're getting smarter every day. It's an area I started looking into when I was preparing this presentation, talking to some of my colleagues about deep learning and how these machines actually think. And it came up with some surprising results. So this is a little bit of a study that was done on deep learning, and how you can fool a deep learning system and some of the fragilities of it. So the image on the left that you see there is a picture of a panda. I think we all agree it's a panda. It looks like a panda. Eats shoots and leaves. Yep, it's a panda. Machine's only 57% confident of that, because what they do is they feed in thousands of images of a panda and tell the machine it's a panda. The machine itself, the algorithm, decides what is important to be a panda. It's not told the rules as we would look at it. It doesn't think it's got a white face, little ears, and black eyes. It's a panda. It does it completely differently based on this one. It's just on pixels. This is just a digital image. If you understand how it thinks, you can attack it. And you can do that by putting these pixels in the middle. Those middle pixels there are merged with that left image to make the right image. It looks the same to me, but it is a merged image. So when we do that, the deep learning algorithm goes from being not confident it's a panda to being pretty certain it's a gibbon. It doesn't look like it. That's because it doesn't think like we think. So these are part of the things you have to consider about machine learning and how complex it is to expect these machines to be able to cope with simple things that we do, like driving and finding a white line, by using artificial intelligence. And here's a real example for traffic signs. This is a deliberate adversarial attack to test a system. So this image on the left is a stop sign. We all recognize it's a stop sign, I'm sure. If you look there, you've got some white and black bits of what look like graffiti. They're not actually graffiti, they're deliberate. They are intentionally placed pixels, really they are. They're physically on the sign. When you feed that into the algorithm that used to say that's a stop sign, those pixels fool it into thinking it's a 45-mile-an-hour zone because of how it thinks. I found this quite entertaining because it's such a clever system to give it so much information and allow it to come to its own decisions. That's how we work. But nobody has taught this particular algorithm what we've learned, and that's the basic rules of why a stop sign is a stop sign. It's unique. It's an octagon. We all know it's an octagon, so that when it's in a different country with different text, or perhaps even faded, it's not even red, it's unique, it's an octagon. In the same fashion that a give way sign is the inverted triangle. It's unique, you know what it is, even when it's faded. This machine hasn't been taught that. So in order for it to process this, it would probably need a secondary algorithm just to double check if it's a red octagon. So that kind of thinking, you get to realize that the more inputs and the more complicated you make it for artificial intelligence, the more difficult you make that process when you could do something simple in the first place. The last one on some of the challenges, this has been around for a few years. This was sent to me by my colleague in Australia, and I did like this. So automated vehicles were tested out in Australia. There's huge amounts of roads, very different environments. And the automated vehicle driving along the road had a massive problem with kangaroos. So what happens when a kangaroo makes its random jumping movements? Because the vehicle is using the vision system and the ground as a reference point, as the animal jumps, it changes the machine's perception of its distance. So suddenly, as it lands, it's much, much closer, and the machine goes, I'm going to kill it. So it stops and panics. Clearly, that can be programmed out, but it's these unexpected and unforeseen things that need work. So moving to sum up, because I am reasonably on time. For a safe system to work, it needs to be simple and there needs to be redundancy. You may need multiple systems to help this machine work, but you need it to be as simple as possible for redundancy. If you're reliant on 15 different sensors and 6 different technologies, suddenly it becomes a very complex system with many failure points. Simple things there, little quotes at the bottom there. First one here from Mercedes-Benz was more about level 4 and 5, and it's fairly obvious. If we want to get to the point where these things can actually drive through our environment safely, we need connectivity. And that's not necessarily here now, and all the things that brings. But on the right there, if we just want to get to level 3 effectively, vehicles need to be able to read the current infrastructure, because there are humans on the road too, and we also need to read the current infrastructure. The last one was a bit more sweary, actually. The CEO of Volvo telling the people in New York, you just need to paint the bloody roads. Because it's fairly obvious. You just do. You can do so many things with technology, and you can expect a lot of OEMs and automotive and the people that make sensors to do so much. But if you think about it, you've got so many OEMs making different vehicle systems. You've got different sensor manufacturers, all vying with different technologies to do the same thing. Yet you could make one change, which is the infrastructure, and just make it a little bit more standardized, and suddenly all of these systems can work better, more quickly. So, summing up, question really, do we think our roads are ready for autonomous vehicles? Anybody think that? Or is the other question, are autonomous vehicles ready for our roads? That depends on where we want to put spend, doesn't it? If we think it's the other way around, then the onus is then completely on OEMs and technology manufacturers to read all of the different scenarios we've got currently. If you think about the infrastructure, then when we're going to adapt that to suit, how? What level of performance is required? We don't even know. What level of performance is required for most of these systems to basically function? That's research that needs to be undertaken, in my opinion. Wet weather is such a significant factor. So many of these vehicles, I know snow is a big deal, but snow is a big deal for human drivers. The simple fact of driving in the wet, you can't have a system that works beautifully in the daytime in sunny California for 2 million miles, but you put it into the UK in the middle of Birmingham in November, it can't function because of the rain. There is a lot to be done, as I've said. Improved input equals improved output is a general rule. Put garbage in, you get garbage out. If we can just make the infrastructure that little bit tighter, that little bit more harmonized, then it will make it a lot easier for the transition to fully automated vehicles. That was me. That was very short, 16 minutes. Thank you.